Monte Carlo methods are not just for statistical estimation and Bayesian inference, they also play a crucial role in optimization problems. When dealing with complex, high-dimensional optimization tasks, traditional gradient-based methods often struggle due to local minima and computational inefficiencies. This is where stochastic optimization techniques like simulated annealing come in. Inspired by physical annealing in metallurgy, this method leverages randomness to escape local optima and gradually converge to a near-optimal solution. What is simulated annealing? Simulated annealing is a probabilistic optimization algorithm that mimics the cooling process of metals. In metallurgy, heating a material to a high temperature and then slowly cooling it allows atoms to settle into a low-energy, stable state. Similarly, in optimization, simulated annealing explores a wide range of solutions early on and gradually refines them as the temperature decreases. This approach is particularly useful for combinatorial optimization problems, such as the traveling salesman problem, circuit design, and scheduling problems. How simulated annealing works. 1. Initialization. Start with an initial solution and set a high temperature. 2. Random perturbation. Generate a new candidate solution by making small random changes to the current solution. 3. Acceptance criteria. If the new solution is better, accept it. If it is worse, accept it with a probability that depends on the temperature. 4. Cooling schedule. Gradually decrease the temperature to reduce the probability of accepting worse solutions over time. 5. Convergence. As the temperature approaches zero, the algorithm settles into a near-optimal solution. Why use Monte Carlo methods in optimization? Monte Carlo-based optimization techniques like simulated annealing are powerful because they do not require gradients, making them ideal for non-differentiable functions. They can escape local minima, unlike greedy algorithms. They are flexible and can handle constraints effectively. They work well in high-dimensional problems where exhaustive search is infeasible. Related Monte Carlo-based optimization techniques. While simulated annealing is one of the most well-known Monte Carlo optimization methods, other related techniques include genetic algorithms. Inspired by natural selection, genetic algorithms use a population of solutions that evolve over time. They involve selection, crossover, and mutation to explore the solution space efficiently. Markov chain Monte Carlo MCMC and optimization. MCMC methods can be adapted for optimization by sampling more frequently from high-probability regions, allowing for efficient exploration of complex landscapes. Particle swarm optimization. This technique models optimization as a swarm of particles moving through the solution space, adjusting their positions based on their own experience and the collective knowledge of the swarm. Applications of simulated annealing in Monte Carlo optimization. Engineering design optimizing mechanical structures, circuit layouts, and materials. Machine learning, hyperparameter tuning in deep learning and neural networks. Finance portfolio optimization and risk management. Operations research, scheduling, logistics, and resource allocation problems. Challenges and considerations. Choosing the right cooling schedule. A temperature that decreases too fast may result in poor solutions, while one that decreases too slowly may be computationally expensive. Parameter tuning. Simulated annealing requires careful selection of step sizes and acceptance probabilities to balance exploration and exploitation. Computational cost. While powerful, Monte Carlo optimization methods can be slower than deterministic approaches in some cases. Conclusion. Monte Carlo methods in optimization provide flexible and powerful tools for solving complex problems that traditional methods struggle with. Simulated annealing, genetic algorithms, and particle swarm optimization are widely used in fields ranging from engineering to machine learning and finance. By leveraging randomness effectively, these methods help us find high-quality solutions even in the most challenging optimization landscapes.